again, I want to thank Ruth Kolb again and all my coworkers who contributed quite a lot to this whole effort. Basically, again, as part of the work that Tetra Tech, we're doing with the City of San Diego, we're looking at many, many parts of the puzzle that goes into developing bioobjectives and, trying to advance the science behind that. And so, I have here in this various nicely colored boxes and circles or whatever, that are some of the different kinds of issues that we have been looking into. So I just talked to you about modified streams. We also have been doing work on perennial, non-perennial, and we've been working with SWRCB and others to try to, tag team on some of this to get a better science involved here. This talk is going to be the causal analysis part here, which again is, usually comes in when you've done your bioassessment and you found impairment, and now you've got to figure out what's going on and what to do about that. I just want to point out, I guess, for the most part, causal assessments, this is a framework. It's not usually a protocol. Maybe it can become one, as Rafi was, I think, trying to talk about, with, maybe at least some sort of a screening causal assessment process. But I do want to point out that there's no necessarily one way to do these, and oftentimes they do become site-specific or reach-specific, and you have to go with the flow, so to speak. Basically, these are often data-driven exercises, but there's variations in that as well. It's a retrospective assessment, meaning that you've already seen impairment, now you got to figure out what to do about it. The hope here, at least that I have, and I know many of my coworkers, is that actually by doing this enough, particularly at least in a certain region, that it could actually work prospectively. That, in other words, once you start to figure out what stressors do what, and where you find impairments because of what stressors or at what levels, you can hopefully use that information prospectively later on to hopefully avoid these kinds of impairments, basically before they happen. So that's the whole idea. So you often use many tools here. This can be very challenging. I mean, people have mentioned this. The one I'm going to talk about here was extremely challenging. And if I had my way, I would have chosen a different site. I wouldn't have used the site. It's very tough. So depending on what you're trying to look at and so forth, it can be very challenging. But there are a lot of tools that you can bring to bear now, and that's what I'm going to talk about. And also, hopefully use this to help restoration activities and recovery potential. I think Rafi mentioned this. For any kind of a causal assessment, you need, your stressor or a candidate cause information alongside with your biological. If you don't have that, it's very tricky, or it's very difficult, let's put it that way, to try to figure these things out. Often multiple lines of evidence are needed. Whether you use the EPA's CADIS framework or anything else, you often need to have different multiple lines of evidence to really know what you're dealing with. And then, as Rafi really very eloquently talked about, the appropriate reference or comparator sites. What are you comparing that test site to? And that's very, very important. So I'm going to be talking about many of those things here with this case study. The Lower San Diego River was one of the several case studies that was done as a pilot by a number of parties, and they identified several potential candidate causes there for the impairment that was observed in the Lower San Diego River. I listed those here. And they also noted some real challenges with the comparator sites that they had to work with. I'm going to be talking here about conductivity. We also looked at pyrethroids, but I won't present that here just because not enough time. So this is a map showing this is the San Diego River Basin. Okay, the ocean's out there. And this is the test site. It's SWRMLS. And then the comparator sites upstream of it, and then further, a fourth one up here, which was Cedar Creek way up there. So those were the sites that were in the original pilot assessment. I'm going to show you a couple of things just to kind of get the picture here, that we're dealing with a site that's very low down on a very big watershed. And so while it's a wonderful integrator site for purposes of water quality monitoring and bioassessment, it's basically integrating pretty much everything that's going on up here. So that's very, very difficult. You already know you're in for trouble because you're going to be dealing with probably many stressors here. So that's one thing. And just to drive the point home again, this is the area we're talking about. So we're right in here. You know, you have, what is it, I-8 going across, 15, 805 here, I-6. This is your pristine urban area, okay? This is just nothing but urban here. You know, you've got a lot going on again. All right, what they found in the previous, in the pilot, you know, and again, it was a pilot, that's all, you know, they couldn't do a whole lot at that point in time. You know, these are some of the metrics they looked at. So, you know, you did see some real effects. This isn't everything. They saw many other things as well. But, you know, the decline in the percent amphipods, which was thought to be a good thing that's declining, mostly hyalella here. The same with the collector-gatherers. The non-insects didn't show a whole heck of a lot. But they had some other metrics also, measures that showed, you know, pretty much impairment at this test site, SWRCB. And what they felt like they had some relationship between conductivity and particularly the percent hyalella or amphipods. And this is the data. So the dark blue bars here is your conductivity, whatever that color is your percent amphipods. And basically they looked at these two here. And if you look at those two, in other words, as your conductivity declines, so does your hyalella. Okay, but it sort of does break down a little bit as you get further down here, where the conductivity is at least as much as it was at this one other site, TWAS 1, but you're now dealing with much lower amphipods. So something besides conductivity must be going on here. So the objectives of our assessment was to try to really to understand better the influence of conductivity. And particularly, we understood that there were some natural sources of conductivity in this watershed. So what's going on with that versus anthropogenic? And we also wanted to look at information from outside the case. In the pilot, they didn't have the time or the funds to look at that. It was mostly within the case, those few sites that I showed you, that they were looking at. And I think Ralph, you mentioned this earlier, that sometimes your best comparator sites are not going to be anywhere near the particular test sites that you have. And we wanted to explore that further. And then look at some other, what we hoped were more diagnostic tools. With causal assessment, you have to have diagnostic tools. And many of the kinds of metrics we often use are often not so diagnostic. They can be affected by lots of things. So we wanted to look a little harder at that. So I'm showing this. This is from actually EPA's CADIS website, and this is the source part of their module. This is their conceptual model for conductivity. And I boxed here in red those ones that both the literature that we looked at and then studies that Amick Foster-Wheeler did that actually showed what's really important here, what stands out in this San Diego River watershed. And that's the underlying geology, somewhat saltwater intrusion, imported water, say from the Colorado. These are all factors. Certainly urban runoff, industry, these are all other factors for sure. But the underlying geology was actually one of the things that they're going to do. And I think John Rudolph might be talking a little bit about this tomorrow morning, right? So he's going to give you a much more lowdown on that. But just not to steal his thunder too much, but basically when you look at the underlying sediments, the geology of these sites, it can tell you an awful lot about the kind of ions and salts and so on that you're going to see in the water. And I'm pointing out down here is where you have that test site, that MLS test site, and that's underlined by marine sediments, which are going to confer fairly high conductivity. So it's no surprise maybe. And actually, when we looked at for the ecoregion as a whole, so this is the entire ecoregion 85 here. That basically, if you can see it, the red dots are the high conductivity sites. The more orangey sites, which you may not distinguish, they're beautiful here, those are also pretty high conductivity. When I say high conductivity, we're talking well over 1,000, 1,500 microsiemens. The green are much lower, well below 1,000, usually below 500. And those are more inland, and they are underlain not by these marine sediments at all, but by much different kind of geology. So, so you have to deal with this too, see. And so while there are certainly anthropogenic sources, there's also some natural sources we have to understand. And when we further looked at this, I would say this is preliminary, we still need to do more, but we found a difference in what the ion, the ion composition was, depending on where you are in the ecoregion. So if you're up in the LA region, this is much more sulfates up here, not so much down here near San Diego. Whereas if you go to chloride, it's the opposite. More sites here are high in chloride, not so much in the LA region. So there needs to be, I think, ground truth more. And I know that with the AMIC Foster-Wheeler study, and John will be talking about this more, they found even within the San Diego River watershed, you have, some real differences in ion composition. So we've all known this in a certain way. The conductivity is, you have to kind of know the ions you're dealing with if you want to look at what's going to have an effect and at what levels. So what about these comparator site thing? So we did look at alternate comparator sites. We used a slightly different approach, but very related to what Rafi was talking about. What we try to do is match the sites that had similar land cover and other factors to our test site on the San Diego River, but where conductivity or TDS, or total dissolved solids, were unlikely to be stressors. They were pretty low. And likewise, we also looked for sites which had very similar underlying geology to that test site, meaning marine sediment sort of underlying that. So it had high conductivity, but natural surrounding land uses. We also looked at things like watershed size and many other factors. What we plan to do or like to do in the future is really use some other tools, some other multivariate tools to actually work with that even in a more rigorous way. But we did identify, based on these things, 5 additional comparator sites, which are located. So just like Rafi was saying, here's our test site way down here. We have comparator sites way up here in Ventura County, but they fit the bill. They're useful. I pointed out 2 of these just to show you. One here, I think this is Hooper Canyon Creek, has a high conductivity, not unlike the test site, but more natural land uses. This is, I think, Piru Creek, which has much lower conductivity, but much more urban land uses and a little larger watershed area, a little similar to the test site. So these are the kinds of things we wanted to try to see, well, how does it pan out then looking at conductivity as a stressor? And so here's just a table just showing you 3 of these. So this is a test site going across, and we're looking at conductivity, dissolved solids, and so on. And then here's Cedar Creek, which is way up in the foothills. And then we have another site here. This is the Hooper Canyon Creek, which has, pretty high conductivity, almost as high dissolved solids as the test site. But when you look at your percent amphipods, it doesn't quite pan out, right? You have 0 amphipods at this comparator site, even though you have pretty darn high conductivity in TDS. So in the parlance of EPA's CADIS, if you're looking at co-occurrence now, it doesn't quite match, and I'll show you that here. So this was now looking at outside the case, looking at our other comparator sites, and there you can see that basically here's our test site, high conductivity, very high amphipods, percent hyalilla. Basically, it's true as you get to much lower conductivity, you have low or no hyalilla. But then you have some sites here which can still have high conductivity, but also no hyalilla. So there's more, in other words, more going on if you're trying to predict that. But with EPT Taxa, on the other hand, we found a much better relationship. There was more co-occurrence here between those 2. So we actually wound up dealing with this much more in other causal assessment analysis. So for example, gradient. We looked at that and found there was definitely inside the case even some relationship. When we look outside the case and we look at other sites, comparator sites, not such a great relationship with EPT Taxa. So again, there's more that kind of needs to be looked at there. And so we use some multivariate analyses then to try to tease this out a little bit more. One of the things we did was the random forest model, and what that basically showed us was that conductivity down here was the strongest factor in explaining much of the and propensity scores. I'm not, because I'm running short of time, I'm not going to get into this, but this seems to be a very useful way of also looking at taxa and just conductivity, or any stressor for that matter, in the context of a lot of other stressors and teasing that out more. And I'm not going to get into this now, but we basically were able to form bins. We call these groups of sites that had varying degrees of other stressors as opposed to conductivity, or were able to tease them out better. And we were actually able to show some relationships here now. We're basically keeping the other stressors sort of more fixed, but varying conductivity, we were able to show some relationships. Not perfect, but at least it looks like a good tool. Basically, I'm not going to get into this too much now, but we had lines of evidence for and against conductivity. Certainly conductivity is a stressor. There's no doubt about it. It's just a question of to what degree, and to what degree is it natural. So one of the things that we're going to be looking at is, what sort of conductivity or dissolved solid thresholds should we be looking at, and what can we distinguish anthropogenic from natural sources. Also looking at basically, looking much closer at the ion composition. And I think, again, John, I think we'll be talking more about that tomorrow. Because that's critical. I mean, we know that conductivity by itself isn't so good unless you know what the ions are that you're dealing with that. And to maybe characterize reference conditions for what we know are naturally high conductivity sites in this region, because that could be very useful for objectives or whatever you're doing. So I think that's it. Thank you.
Any last questions? Or is there any questions for John since you presented his?